Well, I confess, I like to play with this little tricks. So thank you, Sarah, for the presentation. And this is the title that was given to me by the organizers. And I have to apologize because I think it's mainly about galaxies hosting gamma-ray bursts, not stellar populations. And the reason is that because gamma-ray bursts are cosmologically distributed, so you mainly don't see stars. I mean, you do, but I mean, not single stars, I mean, high redshift objects. You probably know this, but I want to summarize that there are two categories. The long gamma-ray bursts are associated with the death of very massive stars, supernovae, core-collapse supernovae, while the short-duration gamma-ray bursts are associated with the merging of compact objects, neutron stars and black holes. So these last up to several minutes, and short ones last a couple of seconds, 3-4 seconds. They are much harder to study, so we know much more about long gamma-ray bursts than short gamma-ray bursts. Today we know about 200 redshifts spectroscopically. The highest redshift is 8.26, is the highest redshift object ever detected, spectroscopically confirmed. The energy is very large, 10 to the 15 ergs, emitted in at most 10 minutes, half an hour, the longest. And this is the equivalent to the energy emitted by the sun over its entire life, 10 gigayears. But most of the energy is coming in something that we can't really detect, which are gravitational waves and neutrinos. And the rate of gamma-ray bursts in a galaxy is 1 over 10,000, 100,000 years. And if you correct for the collimation thing, this could be like a factor of 1,000 or so less than supernovae in a galaxy. So this energy is already corrected for collimation. If it wasn't collimated, the energy emission gamma rays, then we would have a phenomenon that we can really explain. Only annihilation of matter and antimatter will produce so much large energies if the emission is isotropic. So you have emission mainly through jets. This is the redshift distribution, cumulative distribution of objects, quasars were the first high redshift objects. Then galaxies took over a few years ago. But now gamma-ray bursts are more efficient in probing the very high redshift universe. This is the redshift distribution, and the comparison with quasars is a very limited number. And I use log scale here to make it less depressive from the gamma-ray burst point of view. But you can see that you can go much further in terms of distance. And here the limitation is near-infrared observations, but probably not only. It looks that there is a decline in the number of the gamma-ray bursts that we have a very high redshift. And so there are many dark bursts not detected in the optical or X-ray, and people, well, mainly in the optical, and people are speculating that these are dark because of dust or because they are faint objects, and not because they're very high redshift objects. Although
redshift 9?
Yes, this is still very preliminary, 9.3. Yeah. How do you know that? Oh, this is 1 plus Z. Sorry. Yeah, I use this is 8.3, but there is a 9.3. This is not even public. I was surprised you would know this, but there is one candidate. Okay, forget it. Can you cut this? Cut. So the reason why I showed 1 plus Z in log scale is this is because it's proportional to time, which is much easier to interpret than using just redshift. If you use just redshift, you see a peak here and then a sharp decline, which is physically a little bit confusing. So golden age of gamma-ray bursts. So I want to convince you, well, I guess you know already, but that this science is very exciting because in the last 2 years there have been a number of interesting discoveries. And so I'll show a few of them. This is the gamma-ray burst 08 or 319b 2 years ago, and it's the brightest event ever recorded by humanity. It was optically It's called naked-eye gamma burst because for less than a minute or so, it was observable with your naked eye, if you know where it was, and it's that means that thousands of times brighter than the brightest quasar. Then this object detected the same year at redshift 6.7. At that time was the second most distant object, spectroscopically confirmed object ever detected. And a few months later, the highest, most distant object known at redshift 8.26. This is the photometric redshift, but it's also spectroscopically confirmed. Another event, redshift almost 1, very energetic event detected with Fermi, where it was possible to test the invariance of the Lorentz invariance. According to some theories of quantum gravity, the Lorentz invariance has broken a very small scale. That means that some photons, very energetic photons, can have a speed difference from the canonical speed of light. And this is not confirmed by this object here. It means that the speed of light is constant down to 20% lower than the Planck scale. Interesting. So there are a number of discoveries that have been done just in the last 2 years, which is telling you that it's not a cosmic coincidence, or I think we have no reason to believe that, but it tells you that this science is very active, and it's very there's a lot that we can learn using gamma bursts in different fields. So going a little bit back to Earth, or so, there is a we know that gamma bursts are associated with supernovae because after the detection of the gamma ray emission, if you wait long enough, you see the supernova coming out in the optical. This is the first case in 1998. It was discovered, and the spectrum of the supernova that shows you that this object, this gamma burst, is associated with the supernova type 1c. 1c because there are no features here, so no silicon absorption, no helium absorption. And it's very bright, much brighter than canonical supernova type 1c or 1b. And now today we know 6 objects of this type after 12 years. So it looks that the supernova associated, gamma bursts are associated with supernova, at least the long gamma bursts. And some have been spectroscopically confirmed. Many others at high redshift have been confirmed using the light curves. So Andy Fruchter and collaborators a few years ago studied the galaxies hosting gamma bursts at low redshift below 1.2, and compared it with host galaxies of supernovae, co-collapse supernovae, supernovae type 2. And they find that gamma bursts are located in the brightest regions of their host galaxies. This is the cumulative distribution of fractional light in these events. So the gamma bursts are more distributed towards the brightest region of the galaxies compared to when you compare with supernova type 2. This is a striking difference. But the Fruchter et al. Considered supernova type 2, which are different from the supernova type 1c. They're all co-collapse supernovae, but they have different features. So more recently, Kelly and collaborators have done the same analysis, selecting the host galaxies of supernova 1c, and they found much better match. So apparently these events are able to select the galaxies. And these objects are, supernova 1c apparently have lost the external envelope, and this is why they don't show absorption features, silicon features or helium features. And somehow they are